Why don't we get started? I forgot to charge my headset last night, so I'll check periodically to make sure the microphone is still active. But I might switch back to just the regular laptop, which would constrain me to be closer to the laptop to try to get good sound. So nonetheless, today we're going to switch gears a little bit, and we're going to talk about the image domain. And specifically, we're going to talk about image formation today. Now, this material is not from the book. It's from a bunch of different sources. And the image domain warrants its own special treatment because it's really important to understand both how images are formed, how images are represented, and how we extract information from images. It's a unique thing. Now, granted, you could get a whole PhD specializing in so-called image processing or computer vision, and I hope you do. It's an interesting field to be in because there are so many different applications of computer vision, and that also carries to video processing. Okay, so there is a homework that is due on the 11th of February, which is Tuesday at the usual 1 second before midnight. If you haven't started, please make sure you do start on that. Okay. So, throughout life, all stages of life, whether it's infancy, adulthood, or on through the elder years in life, people rely on their sight for gathering lots and lots of information about the environment in which they live. And when you look to the neuroscience, about 90% of all of the information you input is visual, whether you knew that or not. And if you take accounting of all of the sensor receptors that a healthy human adult has, about 70% of the sensory receptors on your body are in your eyes, right? So of all the five senses, 70% of the actual units of sensation, the receptors, are in your eyes. That's quite a bit. When you process visual information, about 50% of the regions of your brain are active, right? It requires a lot of machinery to process visual information. And 40%, which is significant, of people respond to visuals, right? And so, like you see in most of your classes, there are a lot of visuals associated with the points that the faculty and staff are trying to make. So this visual processing mode and imagery, things that you see, is really, really important. So let's take a look how images come to play in biological systems. And this all deals with capturing of light. And so light comes in, and light is just the reflection of photon energy coming from objects in the environment. And this photon energy makes its way as rays that travel through the air. And these rays are captured by your eyes. And your eyes consist of a lens, and that lens's responsibility is to bend or refract that light to try to collect as much light as possible into this organ, your eye. And this light makes its way through the pupil. And you can see sometimes, if you have a cat or, just another person in the room, when it's really dark, the pupils open in effort to try to let more light in. When it's really bright outside, the pupils close to try to limit the amount of light that comes in, because too much light can be damaging to these sensory receptors. Specifically, ultraviolet light is very damaging, which is why you don't look directly at the sunshine, because the sun pushes out a lot of UV light, among other types of light, and that can destroy these sensors on the back of your eye. And so these rays of light come into the eye apparatus, and they land on a set of receptors, types of sensors, if you will, that respond to different frequencies of light, and they line the back wall of your eye. And so in the center of the back of your eye is a very dense, the densest collection of these sensors. And so the more sensors you have, certainly the higher definition the imagery or the depiction of the light and the object from which that light is reflected, the higher the density or the definition, if you will, of the representation of what is being seen or measured from the environment. Now, in the center of the back of the eye is called the fovea. That's the foveal region. And because these sensors, these receptors, the cones, are so densely packed, you get the clearest, most high resolution, most crisp definition of objects in the environment corresponding to light that hits the foveal region of your eye. Away from the foveal region is a so-called periphery, right? And maybe you've heard the term peripheral vision. Now, as you go further away from the fovea, the density of these cones, these sensory receptors, gets smaller and smaller and smaller, and that corresponds to lower resolution sight or description of objects in the environment. So we have this light, it strikes some sensory element, and that sensory element has different densities. And those densities of these collections of sensors correspond to how high definition a description of objects in the environment that you'll have. Okay, and so if we look at the field of view of a healthy adult, and you can try this with your friends, you know, if someone's facing forward, the entire field of view corresponds to the region in front of you that you can see. Now, of course, human beings have their eyes on the front of their face, whereas other animals, typically, you know, higher order predators, tend to have their eyes on the sides of their head. And things that are more prey have their eyes completely on the sides of their head because they want to get a wider view of what's going on around them, because being able to see things could mean survival versus not survival. Okay, so we have the entire range or field of view covering from the peripheral region of the eye on through the fovea to the other part of the peripheral region for the field of view. And this covers a region, if you were to look at it as a sweep around the unit circle, it covers a range of 180 degrees. So that's quite a bit of sight. Then you have what's called the Nir Peripheral Vision, right? That corresponds to, as you get closer and closer to the foveal region of the eye, that corresponds to a cone or field of view of 60 degrees. And so this angle of things you can see corresponding to the near peripheral view covers 60 degrees. And then if you go to the parafoveal, that's a 10-degree cone in the field of view. And then if you look at the foveal part of your eye, right, that densest collection of cones, those receptors, that corresponds to a 2-degree sweep for information. And so the densest representation of objects in the environment visually only covers a 2-degree sweep, which might not seem like a lot, but if you think about it, if you extend your hand about 2 or 3 feet from your foveal region, right, it corresponds to things that you might be able to grasp or manipulate or hold in your hand. And it kind of makes sense that you would want things that you would grasp or manipulate or hold in your hand would have the best description, the most high resolution, high definition description visually, because you want to know as many details as possible for things in which you will be coming into contact. Okay. Any questions about this? Make sense? And so the following slide is sort of a rendering that represents the relative quality, if you will, of different regions in your field of view. As you go from your foveal region out to your peripheral region, you lose representation. Not only is it less crisp, but you also lose color quality, right? And so here we have the center of the field of view. It's much more crisp, it's colorful, it's very high resolution relative to the rest. And as you go further and further out to the periphery, it gets less and less high definition or high resolution. And I encourage you to try this experiment yourself, maybe with some friends or family or whomever. You have somebody face front, don't move your eyes to the left or right, and then you hold up a card or a piece of paper with a certain color and ask this person, what color is this? And of course, certainly as you get closer to the foveal region, he or she will be able to tell right away, this is blue, this is orange, or what have you. And as you go further out towards the periphery, it'll be harder and harder for this person to be able to distinguish. And as you get to the extreme edge, they can tell you that something is there, but they can't tell you really much about it, right? They can see very coarse motion, not be able to tell you colors or anything like that. So, the idea of this foveal region as being really, really important in providing descriptions, high resolution descriptions of things that you come into contact with, things you manipulate. This exists from birth, right? And so there's something called the tonic neck reflex, and all infants, born with it, healthy infants. And you can test for it. In fact, when you make a well baby visit, I remember, my daughter is going to be 8 end of this month. And I remember when we brought her in, some of the things that they test for are these reflexes that are really, really important. And so this tonic neck reflex is very, very important. And so they take the baby, the infant's head, and they turn it very gently and slowly to one side, and the hand will pop up on that side to which they turn the head. So if you turn the infant's head to the right, the infant's right arm will pop up. Turn the infant's head to the left, the infant's left arm will pop up. Okay. So this is what the tonic neck reflex looks like. And if you look at it, well, if you sort of project forward from this infant's eyes, it goes right to where the infant's hand is, right? And it kind of makes sense, because at birth, what are you doing? You're collecting lots and lots of information, visual information, about things you can grasp, things you can come in contact with your hands, things you can manipulate. And so what the tonic neck reflex does, it conditions an infant for learning about things in the environment. Not only do you garner descriptions of things from how they feel, but also you associate how they look. And if you're going to associate how something looks with how it feels when you manipulate it, you want to make sure that description visually is the highest definition, most detailed that you can have. Now, certainly, if you look at it, notice how it's perfectly aligned with the foveal region of vision the hand is of this particular and most healthy infants. Now, of course, this reflex, it comes at a certain schedule, right, a certain age in infancy, and then after a while, this thing goes away. But certainly, if it doesn't go away, and some people who become adults, you might grow up to become a track star. All right, that joke fell flat. Anyways, never mind. So, the tonic neck reflex. And I wrote this slide. So let's take a look at the how this light is collected. So in this diagram, we have an image, and this is a tree, and it's in the environment. And certainly light bounces off of this object, and these rays of light reflect off, and they go off into the environment. And here we have a cutaway view of the eye, and so it makes its way to the lens, and the lens refracts or bends this light, trying to collect or focus as much light as possible to the sensory elements at the back, namely the cones. Now, of course, this light makes its way through the lens and through the pupil and the viridius humor, the fluid that's in the eye, and then it strikes the back side of the eye where those cone receptors are. And you'll notice here, this image is inverted. And in all imaging systems, and many imaging systems, you'll see an inversion of your image when it reaches the back of the plane, or the surface, if you will, that is the sensor element that provides you a representation of this image. And so when cameras were created, essentially they mimicked what happens biologically. Okay, so let's take a look at the camera abstraction of how images are formed. So this is the classic so-called pinhole camera, and it's called the pinhole camera because you have a pinhole representing or abstracting what the pupil would be. Now, if that pinhole is larger, of course, it's going to let in more light. If the pinhole is smaller, it's going to let in less light. But nonetheless, rays of light bounce off of objects in the environment, and they make their way through the pinhole. They cross as they get through the pinhole, and then they strike some surface, a plane, and on that plane, you see a representation or an image of that object. So really all an image is just a collection of reflected light that's made its way through a pinhole. Now in this case, there's no focusing device, there's no lens, there's no mechanism or component whose job it is to try to bend light in effort to collect more and more of this light energy. This is just a box, and in fact, this is something you could do yourself. You just put a pinhole in it, and you get some type of photosensitive material and put it at the image plane surface where the image will form, and you just open up the pinhole, right? And all of a sudden, after some amount of time, you're going to get your image recorded. Okay, and that's exactly what a camera or how a camera operates. So these were early cameras. In fact, photography, I think, was invented around the mid 1800s. And you've probably seen old images where somebody had like a black blanket, and it was covering them and covering a box on one side, and then they would lift the cap off the other side to expose that light energy to some photosensitive surface, or rather expose the photosensitive surface to that light energy in order to record that photograph. This is an actual pinhole camera, and if you see one of these at a yard sale, make sure you buy it. You can go on Antiques Roadshow, and they'll tell you it's worth a lot of money. Now, there are some old ones that maybe are still floating around, but you can buy some brand new ones right now from B&H Photo and Video, not to call out specific names, but there are other camera stores where you can buy new pinhole cameras. And so you'll notice here, you have a piece of paper, right, on the inside, and there's a hole that's been poked into that piece of paper. And then there's a sort of cork or some covering to cover that pupil, if you will. And when you want to take a photo, you have that black plate in the back, so that's going to have some photosensitive materials on it. So usually it's some planar surface, paper or glass or metal, and it has been treated with some chemicals that will change colors in response to being subjected to different frequencies of light, photosensitive material. So then you take that cork off, exposing those rays of light, or exposing the camera to those rays of light. Light makes it into the pinhole, strikes that imaging plane, that imaging surface, that recording material, and you get your image, right? There are other, this is the back of the pinhole camera. And so initially, they were made out of wood because that was an abundant and easy to work with material at the time. And then you have these plates that slide into these slots, and you cover this whole back of this apparatus with a light blocking material so that you don't expose this plate to light that you don't want it to be exposed to. And then you expose the front by uncorking, take your photograph, wait a few seconds, recork it, and then seal up this plate in some light blocking material, and then you're on your way, you go and develop it, and there's your photograph. Okay, any questions about this? Does that make sense? So, in any discussion of images, it's important to understand how images are formed, because that will inform you about how images can change based on a number of factors. Okay, so this is a more modern pinhole camera. You can buy this on something like Amazon for like $20 or $40. It's kind of like a science-y type thing. And in this particular pinhole camera, you use regular like 35 millimeter film, and you open up the pinhole using a little lever here, and you collect that light, and then you can go ahead and develop that film. You don't have to take it to Walgreens or anything like that. There are home developer kits that you can get where you put that film in a dark room so you don't expose it to light, in a canister, add some chemicals, you shake it, go through a process, and you get your negatives from which you can create prints. Okay. So this is another version of pinhole camera, more modern. It's something you can get fairly easily on Amazon and a bunch of other establishments. Okay. So let's take a look at the digital version. In the digital version, okay, well, you have your object that's in the environment, and the rays of light, photon energy, bounce off of this thing. And then it typically employs a lens, and the purpose of the lens, excuse me, is to try to collect as much light as possible. How does it do that? By bending that light. Now, the lens is typically made out of some crystalline material, like glass, and glass and crystals have this property that when light strikes it, the rays of light of different frequencies, they bend inside of this material, or refract is the term used. And so if you can bend this light, you can guide this light in specific ways, and in so doing, collect more light than you otherwise would just with a pinhole. And so you can imagine this lens as being in front of the pinhole, trying to direct as much light as possible into the pinhole. And so this light then makes its way and it strikes the back of your element. And we have a sensor that kind of looks like your back of your eye, and it has elements that are sensitive to different frequencies of light. And so these things are called CCDs or CMOS devices. CCD stands for charged coupled device, and CMOS stands for complementary metal oxide semiconductor. And so essentially, when the different frequencies of light strike these materials, it causes electrical electrons to start moving. And whenever you get electrons moving, you create a current, and you can measure that either as current or voltage. So then we take that electrical activity from your sensor, and then you digitize it. Digitize it means to quantize. It means depending on the value of that voltage in different regions of the CCD, you're going to output a particular number, right? And so that's where you get from something that's analog, meaning some phenomenon in the environment, to something that's digital, which is a numerical description of something measured from the environment. Okay. And so the output of that digitizer, you get an array, usually in 2 dimensions, of so-called picture elements or pixels, right? And that pixel representation, or that 2D array or matrix of numbers, is the representation of an image on digital systems. Okay? All right. Any questions about this? Does that make sense? All right. So we have this digital version of the pinhole camera, and let's talk a little bit about nomenclature to discuss what happens when you want to make a picture bigger or make a picture smaller. So we have the optical center, and the optical center, you can imagine, is the center of the foveal region. And then you have what's called the focal plane. The focal plane is a plane, so it's a 2-dimensional sheet, and the focal plane is defined as that surface such that all those rays of light come together to a single so-called focal point, right? When you bend that light at the lens, it's going to get concentrated, 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 and then eventually each of those rays of light are going to come to a little dot, and that dot is called the focal point. And so the focal plane is that sheet or surface on which the focal point exists. Okay. And so typically it's practiced to define a coordinate system for each of these planes so you can describe what the location is for each of these points in question. So then we also have another sheet or plane. It's called the image plane. And the image plane is that sheet or surface where all the rays come into contact and give you a representation of that image, right? That's what you're digitizing when you compute an image or take a picture. Now, between the image plane and the focal plane, there's some length or distance, and that's called the focal length. And when you take a camera and you zoom it in or you zoom it out, what you're doing is you're increasing or decreasing the focal length. So let's take, for example, if you increase the focal length, right? What happens there? So the distance between the focal plane and the image plane gets bigger and bigger and bigger. And so those rays, when they strike the image plane, that depiction might be a certain size, but if you increase the focal length, that depiction is going to get bigger and bigger and bigger because it's further away from that focal point on the focal plane, and therefore those pixels are going to get spread further and further and further apart, and your image, as a result, is going to get bigger and bigger and bigger, namely you're zooming. Now, for the converse, when you're going more wide angle with your shot, for example, with a camera, you're decreasing your focal length. So what happens when you decrease your focal length? You're getting closer and closer and closer, the image plane, to the focal plane. And therefore, you're going to be collecting a wider cone of energy, and those pixels are going to look like they're closer together. And you're getting a wide area shot. Things are going to look smaller in the image, but you have a wider field of view. Okay? All right, any questions about this? Make sense? So, let's look at some examples. So we start out and you have 18 millimeters. 18 millimeters is the focal length, the distance between the image plane and the focal plane. So when you look at the setting on a camera, let's say it's a manual camera, and you look at the lens itself, you see some tick marks on the lens, and as you turn the lens, you're moving it forward or you're moving it backwards, and you're either increasing or decreasing the focal length, the distance between the focal plane and the image plane. And so this number is the actual distance, i.e. the focal length in millimeters. So we start out and we have a wide area shot, 18 millimeter focal length. And as we zoom in to 24, you'll notice here the field of view gets smaller, but the pixels get a little bit bigger. Now it's not as easily apparent there if you're only going up 6 millimeters, but as you continue to go 35 millimeters, you'll notice here this barn gets a little bit bigger, right? And your field of view gets a little bit more narrow. So you notice here the tree here off to the left, that tree is bigger, and that tree now is at the left-hand edge of the image, and that barn is a little bit bigger. So then you go to 55 millimeters. You notice how big the tree is and the barn is, and of course you have a lesser field of view, and then you get bigger and bigger and bigger, and then ultimately, if you're at 300 millimeters, which is pretty big, the barn occupies easily half of one part of the, either half of the image in its width. Okay. Any questions about this? Okay, so if you are a student of photography, maybe this sort of stuff will be old hat, but certainly professional photographers learn all about how the lenses work, how optics works, all the different effects you can get, and so forth. Okay. And certainly when you have an automatic camera, you have some sensors that are measuring distances to objects in the environment and changing the focal length accordingly based on whatever settings you have on your auto zoom cameras. Okay, so this is another depiction of what refraction looks like in the top half of this diagram. Here we have some rays of light, and those rays hit the lens, that crystalline material. It bends or refracts that light, and then focuses that light or concentrates that light to a point, and that point, the plane that that point lies on, is called the focal plane. And so if you have a very short focal length, a short distance between the image plane and the focal plane, here we have an object, and it has some height. There's some parallel rays, and some rays go in different directions. It gets concentrated by the lens. Here we have the focal length f, and we see the focal point here, and then the image height is a function, the image size rather, is a function of the distance between the focal plane and the image plane. So this is a typical single lens reflex camera, or SLR camera, and you'll notice here you have two series of lenses here, and then you have a beam splitter, a little mirror that directs some of that light energy up into prism, and this prism bends the glass, bends the light 90 degrees so that you can then see it out in objective. And so the other pathway for the light makes its way onto the image plane and provides a picture, but then the pathway of the light that goes up